In the previous video, we looked at series combinations of resistors, and now we're going to tackle parallel combinations. And you'll remember in that video, I made a reference about how modern party lights have a special design to their light bulbs that enables them to be wired in series when normally they wouldn't be. So this parallel combination is how the much older designs of party lights, the ones that had the enormous bulbs, this is how they worked. They were wired in parallel. So again, here's a battery. So let's say we have two resistors in parallel. We'll call this one R1 and this one R2. And again, the idea is going to be that we want to replace the combination of two resistors with one resistor that is electrically equivalent. So first off, it'd be a good thing to check that these are really in parallel and not in series. So we can attempt to see if they're in series, and as soon as we tried running our finger through, we can see, yep, we're going through junctions here. So that is not series. So then the test for parallel is again mapping the potential zones. So when you map potential zones, when you get to a resistor, so this is a little different than when you're mapping it like it was like for capacitors. When you get to a resistor, when you get right in front of the when you get to a resistor, when you get right in front of the resistor, you just jump across like that. And this is because we know that there is going to be a substantial voltage difference across the resistor because you have a big electric field within the resistor in order to be able to drive the current through the resistor. Same deal here, jump in front of that resistor and come back. All right, so everything there is at plus the battery EMF if we assign the negative terminal to be 0. So let's go ahead and map the negative terminal. We'll do that in blue. So mapping the negative terminal out, which we will assign a voltage of 0. Again, same deal, you just want to jump in front of the resistor every time you get to 1. And everything there's at 0 volts. So sure enough, if I look at this resistor, I got one side in red, one side in blue, one side in red, one side in blue. They have matching color pairs, which makes them parallel. And I guess for completeness sake, we can do the same exercise for our equivalent resistance. Like so. And so now we need to think about what does it mean for this resistor to be equivalent to this one. Well, again, this is all going to be determined from the perspective of the battery. From the perspective of the battery, some amount of current I is going to be flowing through it. Same here, same here. Now here, because there are no junctions, the current flowing through here will also be I. But because there's a junction here, some of the current is going to flow through R1, and we already know it's going to go down because we took the time to map the potential zones. We know this is the positive side, this is the negative side. So we will say that we have current I1 going through R1. And similarly, we'll have current I2 going through R2. And again, we know this is the positive side, that's the negative side, or sorry, the high potential, low potential side. So we know current is going to run from high to low. So here we can use Kirchhoff's node law and observe, if I look at this node right here, from Kirchhoff's node law, the sum of all the inbound currents has to be equal to the sum of all the outbound current. So there's only one current going in, and that's the current, that's our current I. Going out will be I1 and I2. Okay, but if I look here, the current I is what would go through our hypothetical equivalent resistor if we wanted to replace the pair with one that did the same job. So by twinkle, twinkle, little star, delta V equals I times R, the current going through the equivalent resistance, I here, which is the same as the current going through the battery here, would be equal to the battery EMF over the equivalent resistance. Similarly, here, what's the voltage difference across this resistor? It's still the battery EMF, so I1 is equal to the battery EMF over R1, and I2 will be equal to the battery EMF over R2. So we can cancel off the EMFs. And if we rearrange it, we see that for resistors in parallel, they add in reciprocity. The equivalent resistance will be 1 over R1 plus 1 over R2 plus and such up to your nth resistor. So again here, the sanity check is that the equivalent resistance should be lower than the lowest resistance in the parallel network. And yes, again, mathematically, this is the opposite of the situation that you have for capacitors. So once again, let's go and take a look at our photo of our single light bulb. Again, it's hooked up to a pair of batteries. That's just so we can have a roughly 3-volt potential difference across the bulb. And again, the red terminals, the red leads are connected to the positive terminal, and the black leads are connected to the negative terminal. Now what I'm going to do is I'm going to hook up another pair of red and black leads to the leads that are at that light bulb right now. So this will give me 2 light bulbs in parallel. And so I want you to predict what will happen to the brightness of both the original bulb and how is the new bulb's brightness going to compare. So pause the video, and when you're ready, we'll resume. Okay, so it appears that there's no change in brightness, and that is indeed the case. This might seem a little counterintuitive at first, but think about it. This is like adding a lane to a road. If you add another lane to a road, you can carry more traffic through the road. And it's much the same kind of idea here. By putting 2 resistors in parallel, if you work it out, the equivalent resistance is half. So that means the current going through the battery is double. And since the 2 resistors are identical, they're going to have to split the current evenly. So the current going through the battery doubled, but then with the even split, that means that the amount of current that went through each bulb remained the same. Okay, so let's wire it slightly differently. So you can see in here the you can see that the leads are jumped off from the upper light bulb down to the lower light bulb. What if instead of hooking the lower light bulb up to the upper light bulb, I instead also ran them straight up to the battery? How would that change things? Go ahead and make your prediction, and then we'll resume the video. Okay, so it turns out that there's no difference. And that makes sense, because remember that Although real world wires have about 1/10 of an ohm resistance or so, for practical purposes, the entire wire is all at the same potential. So the details of exactly how it's all connected together don't matter. You're still going to have the same voltage difference across the light bulbs, and as a result, they will stay just as bright. And in fact, another way that you can think about it, if you're still not happy with thinking about what happened with the current, is that we can remember that the brightness of the bulb also goes as the square of the voltage across it. These bulbs both have the battery EMF across it. Now, the current going through is double what you had for just one bulb, so the battery's going to drain quicker and it's going to get a little toastier. All right, so now what I'm going to do is unscrew the upper light bulb, and I want you to predict what will happen to the brightness of the lower bulb. So pause and get back with me. Okay, it appears that nothing changed with the brightness of the lower bulb. And again, that makes sense because the voltage across it is the battery EMF. All right, so I'll go ahead and, for completeness sake here, I'll go ahead and screw the upper bulb back in and unscrew the lower bulb. I would like you to think about what would happen to the brightness of the upper bulb. Okay, yeah, it's the same as what it was before too. So, super. So let's go ahead and do a example of this with some numbers here just to make it a little more practical. So let's say you have a parallel resistor combination like so. So we'll say this is 2 ohms, 3 ohms, 6 ohms like before. So here they're in parallel, and if you're in doubt about that, we can go ahead and map out the potential zones, remembering that we hop across in front of any resistor symbols we see. So that's all at one potential, whatever that potential is. And this is all at a different potential, whatever that potential is. All right, so each of them has one side on red, one side on green. So yep, they're definitely all in parallel. So now we can say that the equivalent resistance will be 1 over R1 plus 1 over R2 plus 1 over R3. So this will be 1 over 2 ohms plus 1 over 6 ohms, plus, 1 over 3 ohms plus 1 over 6 ohms. All right. When in doubt, put things on a common denominator, I guess. These can all be put over 6 ohms. So I would have to multiply numerator and denominator by 3 here. So this would be 3 over 6 ohms. Multiply numerator and denominator by 2. So that's 2 over 6 ohms. Multiply numerator and denominator by 1. That's 1 over 6 ohms. So we're left with 1 over 6 ohms. Now, let's be super careful here. Don't forget to take that last reciprocal. So this will be 6 ohms over 6, which is 1 ohm. And so again, for our sanity check, is that less than the smallest resistance we've got? Yes. Okay. So we can have more complicated combinations of circuits. And while it is possible to create pathological combinations of resistors that cannot be broken down into series and parallel chunks, a lot of times they can. In a future video, we will take care of the more pathological case. We'll have to do a more careful analysis using Kirchhoff's laws. But for now, let's just look at a case where we can break it down piece by piece. So let's say we've got a circuit that looks like this. So we've got 10 ohms here. Let's say we've got 90 ohms over here, 45 ohms over here, something like that. And then over here, let's say it's 60 ohms, like so. So again, first off, we can ask ourselves, is there any pair of resistors that are in series? Series is easier, you can just add them up, so it's probably the easiest first place to look. Nope, that goes through a junction. So we can try running our finger through some others, but sure enough, no matter what we try doing, they always go through a junction. So that isn't going to work. So none of these are in series with each other. So then the next question is there anything that's in parallel? And the answer here is yes. So we start mapping out the potential zones for this. There's one zone. Let's go ahead and do another zone down here. All right, and then there's one more zone to be mapped out. Oh, what's a good color? How about purple? Sure. All right. So then you look and ask yourself, are there any colors, are there any pairs of resistors, a number of resistors that have matching pairs of color zones? Okay, so here I've got red and purple, red and blue, so those are not in parallel. Here I've got purple and blue, red and blue, nope. Purple and blue, red and blue, nope. But here I do have purple and blue and purple and blue. So these are in parallel. So with those being in parallel, we can find the equivalent resistance of them. So this will be 1 over R1 plus 1 over R2. So this will be 1 over 90 ohms plus 1 over 45 ohms. So again, let's see, we can put things on common denominator of 90, I guess. Yeah. So this will be 1 over 90 ohms plus, common denominator, plus this would be 2 over 90 ohms, right? So this would be 1 over 3 over 90 ohms. So now we take the big reciprocal. We are left with 90 ohms over 3 is 30 ohms. All right. So what we can do now is we can replace this parallel combination here that we were looking at with its equivalent. So then we will have 10 ohms here, and now we replace it with the equivalent 30 ohms here, and then we still have 60 ohms here. All right, so as often works with these things is once you find like a series or a parallel, you flip back and forth. So you should next expect to find something in series, and sure enough, if I run my finger through these, there's no junction here. So this pair is in series. So for that series combination, we can say that R equivalent is equal to R1 plus R2. Well, that'll be just 10 ohms plus 30 ohms is 40 ohms. Okay. So we can now replace this series combination with a 40 ohm resistor. So now we have 40 ohms, 60 ohms, and they are indeed in parallel, but we can always draw the potential zones just to be double dog sure about that. Okay, red and blue. Yep, red, blue, red, blue. They are both in parallel. So we can write this as R equivalent is 1 over R1 plus 1 over R2. So this will be 1 over 40 ohms plus 1 over 60 ohms. So again, let's try to find a common denominator here. 120, right? Yeah, that'll fit the bill. So then over 120 ohms, I would have to multiply numerator and denominator by 3 to have a 120 for the denominator there. Multiply numerator and denominator by 2. All right, so then this is 1 over 5 over 120 ohms. So that works out to be 120 ohms over 5, which is 24 ohms. And as I mentioned, it is possible to have situations that are sufficiently pathological that you can't find individual any individual subnet that's either in series or parallel. For those cases, we'll have to use the full machinery of Kirchhoff's laws. That will be the subject of a future video. So catch you in the next ones.